So let's go now, I sketch the polar graph of an equation like this. And let's identify all values of theta for which my tangent lines are vertical, and which values of theta give me tangent lines that are horizontal. And by the way, let's also play around with drd theta and talk about the difference. Now, I don't know how you were raised to sketch this polar graph. Maybe you just memorize the fact that if r is equal to a plus or minus a times the sine or the cosine of theta, you get a cardioid. That's fine. You might plot points. Personally, I don't sketch the polar graph right away if I can avoid it. I sketch its rectangular graph first, only because this rectangular graph is so darn simple. So what I mean by the rectangular graph is this, treating this as my independent variable, that is my dependent variable. So I will label my horizontal axis as such, my vertical axis as such. And I'll draw one cycle of the curve. Now, it certainly is a case that that's a sinusoidal wave. In particular, it's a cosine wave. It's going to max out at 3 and min out at -3. Now it's inverted. Now it's translated up 3 units. So now I'm going to max out at 6, min out at 0. That being the case, because the cosine wave is inverted, I'm going to start and end one full cycle over 2 pi units on the theta axis at the local min r values. Halfway through, I'll attain my local max. And 1/4 of the way through, as well as 3/4 of the way through, I will attain my median r value. And so here's one full cycle of the cosine wave. Now that's a rectangular graph, and I asked you to sketch the polar graph of this equation. And when I say sketch the polar graph, I mean this. In the xy coordinate system, treat a specific combination of theta r values as theta being the angle you point in, that is the angle I'm making with the polar axis, and r is how far I travel from the polar, or from the pole. So let's just do this. All unitized by 3. Now, as I rotate from 0 to pi½ radians, notice how my r values increase from 0 up to 3. So rotating from here to here, r values increase from 0 to 3. I'm spanning out that portion of the curve. Now, unlike other parametric curves, I don't have a tendency to come in here and identify to the reader the orientation of the curve. Now, as theta continues to rotate 1/4 rotation from pi½ to pi, notice how my r values continue to increase from 3 to 6. So rotating from here to here, my r values increase from 3 all the way up to 6. That point right there literally has polar coordinates at 6, pi itself. I have a tendency to use brackets instead of parentheses, but I don't care if you do or do not. Now continue to rotate another 1/4 rotation from pi to 3 pi-halves. Notice how my r values change direction. They decrease from 6 down to 3. And then the last 1/4 rotation decrease from 3 down to 0. There I get my standard cardioid, which you identify with so easily if you just walk into the Guitar Center. All right, I think I'm going to go ahead and get rid of this so I can have some space. So remember the questions I asked? For what values of theta is tangent line vertical, horizontal? Well, to find out whether tangent lines are horizontal, I'm going to take that numerator I had in that dy dx business. That is to say, I'm going to take a peek at dy d theta, where I had already computed, if you remember, as this. So I'll find this expression, set it equal to 0, and solve for theta. And so I think that gives me the following. So drd theta is going to be, is that a +3 cosine or sine theta? So this factor, the first factor of the first term is this, times sine of theta, plus r times the cosine of theta. And I'm going to set that equal to 0. That being the case, is that going to give me this? Is that going to give me this? I will simplify. Continue to simplify. Oh, look at that. It factors so nicely. And which one's positive? Would that be, so that's going to be negative. Here's positive. Now, that being the case, I do think it suggests, I'm running out of room, can I not write this? That the cosine of theta is negative 1/2. That means my angle in standard position is going to be in the second and fourth quadrants. I misspelled, second or third quadrants. And the angles in those two quadrants whose cosines are negative 1/2 are certainly going to be these two. And within one full rotation, I think there is only one angle whose cosine is positive 1. That'll be 0 radians, or you might say 2 pi radians. That being the case, I've got my candidates for having a, so this one's going to be horizontal tangent line. So looks to me like my tangent line is going to be horizontal here. Theta being equal to 2 pi thirds. Or here. And that angle, I won't write it in, but it's 4 pi thirds. I also have 0, but something kind of funny is going on here with that little cusp with my cardioid. So technically speaking, you know what's going to happen with dx d theta. It's going to be 0 and theta is equal to 0 as well. That's why I said earlier, just because this piece is equal to 0 for some value theta, doesn't mean those values of theta give you a horizontal tangent line, because if dx d theta is equal to 0 for the same theta value, something like that's going to happen. Okay, so let me get rid of all these markings. Now let's identify what values of theta give me a vertical tangent line. Let's go backwards. All right, it's going to happen here, here, and here. So let's dive in and see what happens when I try to derive x with respect to theta, the denominator of the dy dx on the other side of the board. So it can be this. All right, let me contain this board a little bit. So substituting everything in and then setting this equal to 0, we'll solve for theta. So dr d theta is this. I can't do it for some reason. 3 times sine of theta times the second factor of the first term minus r times the sine of theta. So what shall we do next to solve for theta? Oh my goodness. Here's what we'll do next. We'll correct my clumsy mistake. You know, distributive is multiplication over the addition. Isn't that last term rather this? Uh-oh, ran out of room again. I said rather this. Now, that being the case, looks to me like I can combine a couple of terms as such. Factor. And here too, running out a little bit of room. Do you mind if instead this time I just dive in and identify these theta values? Certainly this first factor is going to be 0 when theta is equal to 0 or pi radians. But the cosine of theta is positive 1/2 when theta holds these two values, giving me angles in the first and fourth quadrant. Now again, earlier we found out that dy d theta was equal to 0 and theta is equal to 0, so I'll reject that one. And I think it's for these three values of theta. Here, here, that angle, which is pi thirds, here, an angle of 5 pi thirds, for which my tangent lines are vertical. So let's unify dr theta when theta is equal to 2 pi thirds, and let's just say something, say anything we can about it. Well, dr theta, we've already computed twice. Was it this? And therefore this is equal to this. And it's not 0. So let's analyze what this number is really telling us. Because I think when theta is equal to 2 pi thirds, that's where we found a point at which the tangent line was horizontal. But that's not equal to 0. The reason why it's not equal to 0 is because this does not represent slopes of tangent lines in the xy coordinate plane. It might represent slopes of tangent lines in the r theta plane, but that's not where we're living. So I think what this is really telling me, since it's some positive number, is that as I'm rotating, locally speaking, about 2 pi thirds, going from a little less than 2 pi thirds to a little bit larger than 2 pi thirds, the average rate of change of r is kind of like this number. Or shall I say better, the instantaneous rate of change, or even the instantaneous increase in r, is given by that particular value since it's positive. So I'm just trying to shake you up, make sure we all understand this does not represent necessarily anyways the slope of a tangent line in the xy coordinate plane, albeit sometimes you're going to get lucky.